Welcome to a video lecture on the photoelectric effect. This one will look at the particle nature of a photon and the fact that it emits electrons when it is incident on some subsurface. We will be looking at this from chapter 29, and we'll move through sections 29.3 onward. So let's get started. The photoelectric effect occurs when photons are incident on a surface and have enough energy for that surface to emit or cause an electron to be ejected. This electron is then shot off with some remaining kinetic energy due to the extra energy left over from the photon, which we'll talk about in a second. While I understand this is slightly confusing. This is used frequently in charge-coupled devices, anything that requires an amount of charge to be released by some, the reverse, some amount of light to be released through that. So there's also a lot of detectors that are used for this to determine the amount of photons incident in some area or intensity of light. Couple of little just ground rules for the photoelectric effect. First, this is for light or UV light or infrared light, so visible light within that range. There's different interactions that occur, or we talk about different interactions that occur at higher levels of electromagnetic waves. So these photons are all electromagnetic waves, and under this point of energy is where we see the photoelectric effect, which deals with light. So, but they need to be hit the surface with a high enough frequency or a high enough energy to be able to eject an electron from that. The electrons, while they're called photoelectrons, same deal, no big worries. We view photons as a wave packet. And what this means is they once again have that particle and that wave effect, so we call it a packet of waves. And this packet has a set energy that depends on the frequency of the wave, because for a photon there is no rest mass, because there's always a kinetic energy, it's always moving. And we talk of this energy is related to the frequency, and frequency can be found by taking the wavelength, the speed of light, and dividing it by the wavelength of the set light. So the speed of light, 3 times 10 to the 8th meters per second, divided by the wavelength. So we know frequency, and multiplying the frequency times what's called Planck's constant. Now Planck did his work in black body radiation, looking at how these curves fit, and determined this constant, Planck's constant, which is 6.63 times 10 to the negative 4th joules per second, which really doesn't mean much in that sense of a unit, but there it is right now. So we're going to talk about it a little bit more in a second. So, but there it is, Planck's constant. The energy contained in a packet of photons depends on the frequency and Planck's constant. So jumping back to something that we didn't use a whole lot, and now we will, the electron volt. The electron volt is a unit of energy. It's the amount of energy needed to move one electron through 1 volt of potential difference. This is used with small particles like protons, electrons, photons, anything like this. It has the equivalency of 1.602 times 10 to the negative 19th joules. And so it's a very tiny amount of energy as we're talking about here, but when you talk about lots and lots and lots of electrons or lots and lots of interactions happening at one time, then it becomes very large. And we often see these talking about in bigger forms of unit, the mega electron volt. So this is a 10 to the 6th electron volts, and it's one more step to go through and convert everything. Now, when a photon is incident on some surface, if it has a high enough frequency, which relates to the energy, so if it has a high enough amount of energy, then the electron that will be ejected will have some sort of kinetic energy. We know the mass of an electron, we can determine the speed from that, but there's some kinetic energy that the electron can have, and this is really a maximum electron. Now, if the incident photon, is less than what we call, and this is what we call the work function, the minimum amount of energy needed to eject an electron. But this is a minute. If the photon has a frequency or an energy, either one, they're the same thing, less than what this work function is, then no electron is emitted. So you can shine that light on there for as long as you want, nothing will happen. But as soon as you go over the minimum frequency, what you start to have happen is you start to have electrons are ejected from the substance. Now, this follows along with the conservation of energy, which I think, and I'll go against other teachers and other people, I think is the most important concept in physics, more important than Newton's laws and whatever you have, because it works on both a microscopic and a macroscopic. So it works, you have conservation of energy within a roller coaster, you have conservation of energy within the photoelectric effect. You have this, energy is always going to be conserved. So you have some amount of incident photon energy. This is calculated by Planck's constant and the frequency. This is equal to the work needed. This is the work function needed to eject an electron, and whatever the kinetic energy is for the excited electron afterwards. So this photon comes in, it is able to eject an electron, and it provides that electron with some amount of kinetic energy afterwards. So the AP version is a little bit different than this. It's just rearranged. So it says that the kinetic energy maximum for the electron is equal to the energy incident from the photon minus the work function. So here we have a quantitative example of the photoelectric effect. We have potassium, which needs 2 electron volts in order to eject an electron. And we have different types of photons of different wavelengths incident on this potassium sheet. And I'll go through some calculations and show them step by step in the next slide, but let's look here for a second. We have the incident light here, the red, 700 nanometers. It has about 1.77 electron volts of energy. It doesn't have enough energy to eject an electron. Next, we have the green light, about 550 nanometers. It has 2.25 electron volts of energy. That's more than enough of the work function needed to eject an electron. So we can use that to find the remaining energy, and from that, that kinetic energy, the maximum amount, the maximum velocity that this electron could have, we could calculate that out by using 1/2 mv squared, and we can find the velocity. And finally, we have the blue light, which is what you'll be calculating out tonight for your homework to do the problem online. Is we have a 400 nanometer light. First, you're going to have to find the energy of that light, and then you'll have to find the maximum velocity that is of the ejected electron. All right, so how do we go through this step by step? First, we're given the wavelength of the light packet, of the incident photon. Now, this wavelength corresponds to a set frequency, which we can calculate with speed of light divided by the wavelength is equal to the frequency. So we can first calculate the frequency, as I've done here. Next, we move on to calculating the energies in this light packet. This is done by Planck's constant times the frequency. Second step, done there, we get 2.25 electron volts. I've rounded a little bit, so we're moving on. Next, we need to find the maximum kinetic energy of the ejected electron. Keep in mind, this is all for the green light. We use the energy of the incident photon, that we've just calculated, minus the minimum energy needed to eject an electron, and we get 0.25 electron volts. Once again, rounding, so you may get something a little bit different. In order to calculate this, we need to convert this once again back into joules. As you've seen, I've done this a couple of times. I've switched around. Or we could have done it just one time and converting the 2 electron volts needed into joules and gone through that way, which may have been a little bit easier, but I just decided to follow along with it in this step. Once we have the maximum kinetic energy, that is needed in joules. We can then use the mass of an electron, which you have in your textbooks, to go through and calculate out the velocity, because the velocity is 2 times the kinetic energy divided by the mass of the electron, and you take the whole square root of that. So what I'm going to ask you to do for your problem is calculate the wavelength, using the wavelength, calculate the maximum velocity of an electron ejected by some blue light with a wavelength of 400 nanometers. All right, 2 questions. What is an electron volt? And for this, I'd also like you to say what is the equivalent of an electron volt also. So just what it is and what is its equivalency. And then finally, the calculation question that I've talked about and referred to earlier, what is the maximum velocity of an electron ejected from a potassium surface with a work function of 2.0 electron volts due to blue or violet, whatever you want to refer to it as, incident light that has a wavelength of 400 nanometers. I've done this problem out for almost 75% of the way done, that you can go through and do this out on your own now. So, thank you very much. Have a good night. See you tomorrow in class.